Alright, so this video is gonna give you some suggestions and hints as you complete the pre-lab and the report for the chemical reactions lab. So I'll start with the pre-lab questions, right? And they ask you to summarize the 5 different reaction types that you see here. And in most cases, as you probably realized, the answers to the pre-lab questions are actually in the lab itself. Okay, so if you scroll back, the first couple pages of the lab handout describes those types of reactions, right? So you have your start up here with your single replacement, your double replacement, your decomposition, you have your combustion, and you have your ionic equations. All right, so you want to make sure and go back and read those sections to describe and summarize those different types of reactions. In number 2, you're asked to describe an ionic equation, right, and how to actually write an ionic equation. And again, there's an example, or actually several examples of these in the pre-lab. So if you go up to this section here, all right, it talks about your ionic equations and what happens when these substances that are aqueous actually dissolve in water, right? So what this is saying is that if you have something like potassium, we'll take the potassium sulfate example, right? Aqueous means dissolved in water. All you're doing in these ionic equations is you're just separating the ions. So separating into the ions. So in other words, you're doing the opposite of what you did a couple of weeks ago when you put the ions together to make that ionic compound. So the question then is, what are the ions that are produced when potassium sulfate dissolves in water, right? When it's in solution. So in potassium sulfate, the name kind of tells you what's there. You have potassium and you have sulfate, SO4. These are both going to be dissolved in water, so they're both going to be AQ. So we have to figure out now what the charges are on these things. Well, you can use the technique that we talked about in lab a couple of weeks ago. For potassium, you can look at the periodic table. It's in group 1, so the charge is going to be +1. And then sulfate is an example of a polyatomic ion, and that's on your polyatomic ion list that has a charge of -2. From the formula for potassium sulfate, right, this tells you that you actually have 2 potassiums for every 1 sulfate. So it actually need 2 in front of the K+. So when you write your ionic equations, the subscripts, right, tell you how many of each of those ions you actually have, right? The subscript here for the sulfate, right, is just 1, so we only have 1 of the sulfate on the right side. If you look at the other examples down here on the left side, right, you'll see magnesium nitrate breaks into magnesium. We can predict the charge based on the group number being +2, and then the nitrate, the subscript of 2, tells us that we're going to have 2 of the nitrates, right? So the subscripts then of the ions become the coefficients, or the numbers in front of the ion that indicate how many if they have when they undergo dissociation. So the other thing to keep in mind, especially when we're dealing with polyatomic ions, because some of these are going to have the subscript as part of the formula, right? So in that case, the subscript here of the 3 in the nitrate does not become the coefficient, because the 3 here is actually part of the chemical formula for nitrate. So similarly, in the potassium sulfate over here, that 4, right, is part of the chemical formula for sulfate, so that does not become a coefficient. Okay, and then the second page of the pre-lab questions are things that the first question are things that we did a couple weeks ago, right? So here we're just putting together now these combinations of ions to make your ionic compound. numbers 4, 5, and 6, all right, those are the answers to those are in the lab reading itself. And we talked about those in class, specifically the 4 states, and then the results of the flame test are summarized in the lab experiment itself, and then the safety concerns for 2A that you actually did in lab. Number 7 is the one I want to focus on a little bit. So it says elemental magnesium, all right, so you should be able to figure out what the formula for that is. So it's just magnesium and it's a solid. And then hydrobromic acid, right, is just like the hydrochloric acid you used in lab. So hydrochloric acid was HCl, hydrobromic would be HBr, and that's going to be AQ, right, because it tells us that it's aqueous. And as the reaction happens, it says the magnesium metal dissolves and a gas is evolved or produced. And then they test the gas and it gives you that characteristic pop, right? So now we know what that pop means, right, on the base on with respect to the identity of that gas. And then we can take a look and see, we can come up with the ionic equations for all the aqueous reactants, right? So the aqueous reactants would be your HBr. That's AQ. And you want to break that down into its ions like we mentioned previously. So it says based on the results of the flame test, right? So your flame test here will tell you that hydrogen, right? The pop tells you hydrogen gas is being produced. List the chemical formula of product, and then based on the remaining ions and elements in the reaction, what is the formula of the compound made from the leftover elements? All right, so the hydrogen comes from this part of your HBr, and what we're left with then is the Mg, and we have the Br minus, right? Because in your ionic equation up here, that breaks down into H plus and your Br minus. So this becomes your gas. So what you're left with is your Br and then your Mg, and your task then was to put those together, right? So you end up predicting the charge on the magnesium, right? Magnesium's in group 2, and then your bromine, you know the charge on that one, and then we're going to combine these to give the correct chemical formula. So then you can write the skeleton equation, all right? So the skeleton equation would be similar to the one that I demonstrated to you in lab, where we tested it with the glowing splint and it gave you a pop with a squeak. So you have your magnesium solid reacting with HBr, AQ, and now we know that that produces hydrogen, which is the gas, and then we also get your Mg, Br2, which would be the combination of these two things. And then that's your skeletal, and then you would need to balance, right? So this is unbalanced. And this would be an example of a single replacement where the Mg kicks out the hydrogen, and the magnesium takes the place of the hydrogen. All right, and then for the actual data that you collected, all right, so for the single replacement reactions, right, hopefully you wrote down the formula of each of the reactants, right? They were on the vials, the labels on the vials, and then you made your observations. What did you see? Bubbles, solids, etc. And then you want to describe the products, right? So what were the products that you actually saw? Did you see a gas, for instance? Did you see solids, etc.? Similarly for part 2 and the double replacement reactions, right? So you would have had to have recorded your reactants when you were in lab, and then recorded your observations, everything that you saw, right? Color changes, gas formation, what else? Solids, etc. And hopefully your observations are very descriptive. In part 3, the demo that I did for you, where we burnt the magnesium, all right, so there the reactants were magnesium, and then it also combined or reacted with oxygen gas, O2G, right? Those were your two reactants, and then you write your observations, whatever it is that you saw or heard or experienced when I did that demo for you in lab. Okay, and then for the questions, all right, this is where you're putting together now some of the stuff from the pre-lab and what we talked about in class to make some sense of what you actually observed. So in the part 1 question, the first question here asks you to write the ionic equation. Okay, so now we know a little bit more about what that means. All we're doing is taking our compounds here, they're aqueous, and we're going to split them into their component ions. All right, so for instance, the copper sulfate, right, aqueous, is going to break apart to give you copper. And we're also going to get the sulfate. All right, remember now the sulfate is 2-, which means the copper then has to be 2+ to cancel out that charge. So we're just deconstructing, in other words, the ionic compound to turn it into the ions. Based on what you actually saw in the products for the test that you did, so either the products that you observed or the chemical test that we did, you want to list the remaining ions for each tube that haven't been used to form new compounds. So for example, in test tube 1A, right, that's the one where we saw that hydrogen was produced, right, and what's left over would be the other components from the reactant. So in test tube 1A, we had our zinc reacting with our HCl, right? So what was produced here was hydrogen, which was this part of it, right? So that became H2. So what we're left over now is the zinc, and then we also get our Cl, right? So your task would be to use these and combine them to make a new chemical formula. And you're going to do that with each of the tubes where you did see a reaction. So if you did not see a reaction, then you just write no reaction. All right, so if you didn't observe a change, write no reaction. No reaction observed. So based on the ions that are left over, we can combine these to make our compound. So in the case of the zinc and the chloride, we end up making zinc chloride. And then what we're going to do is put everything together now to write our chemical change, chemical reaction that actually happened. So in 1A, for instance, right, we started with zinc metal, which was a solid, with HCl, which is aqueous, and now we predicted our products, or we determined that we had H2 based on the test, and then we also saw based on our combination here that we made zinc chloride, which is aqueous, right? So this is your unbalanced equation. You need to go ahead and balance that. I'm not going to do that for you. I think it's good practice for balancing equations. All right, and then number 4 just asks you to make some sense of the observations that you made from the single replacement reactions. Part 2, the double replacement reactions, right, asks you to write the ionic equation for the dissociation or the breaking apart of the ionic compounds. All right, so I'll do one of these to kind of remind you of how to do this. So all we're doing is breaking it down into its ions. So sodium phosphate is made up of the sodium ions, and we have the phosphate ions, PO4. All right, so the subscript here for the sodium becomes the coefficient, so that means we'd get 3 of the sodium ions, and then we just have 1 of the phosphate, and remember phosphate is -3. All right, that's all you're doing for each of these ionic compounds. So you can do the same thing for the first thing you put into the test tube, so nickel chloride. That would break down to give you nickel, and then we also get the chloride ion, right? So the subscript here for the chloride becomes the coefficient for the Cl, and then the nickel there, then because we have 2 chlorides, the nickel has to be +2. All right, so we're again just splitting it apart. So based on the ions that you produced here for each test tube, then we can take those and use them for number 2. right? So it says based on the products of the chemical test, pair the remaining ions with each other to form a new compound and use the remaining ions to make a new chemical formula, right? So in the case of our example above, right, originally we had the sodium and the phosphate paired together. Now they break apart individually. We had the nickel chloride paired together. Now they break apart. So all we're doing is we're going to swap these ions and anions. So the sodium now is going to go with the chloride, and the nickel is going to go with the phosphate. And what you have to do is just to combine them in the right ratio, so your ionic compound then ends up being overall neutral. So the nickel goes with the phosphate to make the nickel phosphate, right? And again, the subscripts tell you the ratio that they need to be in, and the sodium pairs up with the chloride to make sodium chloride. So what happens are the metals are going to swap places with each other, right? That's your double replacement reaction. So based on the products that you predicted from the original equation up here, right, and based on the combination that you originally put into the test tube, then we can go ahead and write a basic or a skeleton equation for what actually happened, right? So you mix together in 2A nickel chloride with sodium phosphate, and we just predicted what the products would be by swapping the ions. We get the nickel phosphate and we get the sodium chloride. All right, so you write your skeleton equation, and then you can go through and you can balance your equation, right? So again, you're going to get good practice balancing these equations, and they're going to have, many of them are going to have the polyatomic ions in them. So based on your observations for the double replacement, then we can go ahead and summarize those to answer your questions underneath. In part 3, remember that's the one where you heated your the blue copper sulfate hydrate. All right, this was a blue solid that you heated, and you should have observed a decrease in the mass, right? So think about this compound, right? It looks a little weird in terms of the formula. This part of it here that comes after the decimal point, this tells you that there's water as part of the structure. So when you heat it, what do you think is going to happen to the water? Right? It's probably going to leave, it's going to vaporize. So you actually change the chemical formula for the compound. Right? So essentially what's occurring here is you're going to start off with your copper sulfate. We're going to heat it, and as a result, this breaks down. We drive off those 5 water molecules. Right, those end up leaving as water vapor, and then we're left with just a solid copper sulfate. Right, so the type of a reaction we're looking at is when we start with a compound and it breaks down now into more than one, or it breaks down into 2 or more products. That type of a reaction has a particular name associated with it, and that name is in your lab document, right in the first couple of pages. So after you heated your sample and you weighed it, then afterwards you added some water to it, right? So think about what actually you observed in that reaction when you added the water back to the solid, right? You probably saw that the color changed and it looked really similar to what you actually started with, right? So you want to process that in terms of the identity of that substance that you created at the end, right? So when you heated the blue solid, you drove off the water and it changed color and it changed texture. And then afterwards you added water back in and it changed color and texture again to look similar to what you started with, right? So when you added the water, you just did the reverse of that process. So the reverse of breaking down is what you did when you added the water back to your dried product. Okay, and then for the last demo that I did for you, the burning of the magnesium, right? So here, this one I did write this reaction out for you in lab, so I'm not going to revisit that one. You should have written that down. So this is from lab. Equation, right? And we talked a lot about that one. I explained it to you in terms of what was happening to the magnesium and the oxygen. What I will do is I will also do a short video that covers the different reaction types that will address some of the lecture aspects of the lab. So stay tuned for that video about different reaction types.